Okay, great. So let's start. Welcome everybody to the Israeli Algorithmic Game Theory Seminar. Today we are delighted to have Kira Goldner from Columbia University, and she'll talk about online multidimensional gains from trade maximization. So welcome, Kira.
Okay, I think I can see everyone in the chat, so feel free to ask questions in any way possible. I'm sure you'll interrupt if you want to. Okay, great. So hopefully we're all basically familiar with one-sided markets. We have a bunch of buyers. They have values that are drawn independently from prior distributions, which are known to a seller, and the seller designs a mechanism. The seller may have multiple items to sell. They may be different types of items, a red item, a green item, a yellow item, and the seller can design a mechanism to maximize revenue, maximize buyer welfare. We know a lot about how to sell items in one-sided markets. Today, we're going to talk about two-sided markets. What's different here is that in addition to having a bunch of buyers with their values, we also have sellers who have their own values or their costs for the item. The sellers are endowed with items. They might have one item each. They might have a set of items each. They could be identical. They could be different. And we'll have a platform in the middle who is now the mechanism designer. The designer is no longer just the sellers. It's a separate platform who needs to coordinate the incentives of both the buyers and the sellers. And for this whole talk, we're going to assume that all of the values are drawn independently. So we'll have seller values drawn from various seller distributions, buyer values drawn from various buyer distributions, and they'll all be independent, okay? And the platform's job is to decide how should we allocate the various items from the sellers to the buyers. Okay, we see two-sided markets everywhere, from the stock exchange to DoubleClick, where websites are selling their ad slots to advertisers, Amazon, eBay, Uber, Airbnb. They're extremely prevalent. One of my motivations to work on this problem is from online labor markets, where we have workers on one side who are the sellers in the setting, selling their labor. And on the other side, we have employers who want to buy labor. So workers sell their labor, it costs them some value to produce their labor, and employers want to buy the worker labor, and they have some value for it. And so here the objective is to maximize the value of the matches, or the platform's value of the matches. And so this is part of a larger agenda on social good that I have that I'm not going to talk about today. What is our objective here? Our objective is going to be efficiency. For now, I just want to start with the setting that there is one type of item. Every seller starts with one item, and every buyer wants at most one item, just to illustrate the basic concepts. So the platform needs to decide how should it match the various sellers and their initial item to the buyers who are going to then buy that item. One objective could be social welfare. So what is social welfare in the two-sided market? Well, welfare or post-trade welfare is just the sum of the values of who gets the item after the trade. So if the buyer winds up with the item after this allocation, we count their value. If the seller doesn't sell their item and they keep the item, we count their value, okay? Another way we could write this is we could just write the sum of all of the seller initial values and then write the gain of the new buyer values who get matched. So this M here is who gets matched in this matching. And now the new buyer values who bought the item minus the seller who no longer has the item. We can also call it the pre-trade welfare before we match anything. Since before the trade, every seller just has the item, then the welfare is just all of the seller values. So the gains from trade, which is the objective I'm going to talk about today, is just the post-trade welfare minus the pre-trade welfare, which is just this buyer value of who bought the item minus the seller's value of who initially had it. So what that means is that we can write that welfare is equal to, this is post-trade welfare here, is equal to gains from trade plus just all of the seller's value. What does that mean? That means that, first of all, maximizing welfare is equal to maximizing gains from trade. If we get the optimal of one, we get the optimal of another, because this doesn't change with the allocation. This is just seller values. Neither of these, this does not depend on the allocation. Both of these depend on the allocation. If we approximate welfare, we do not approximate gains from trade. But if we approximate gains from trade, we approximate welfare because of this extra added affine part. Okay? So gains from trade is harder to approximate than welfare. And any approximation results for welfare do not imply an approximation for gains from trade. Okay? And so just for an example, suppose we have a setting with just one buyer and one seller. This is called bilateral trade. Suppose the buyer's value is 5 and the seller's value is 4. So just for a sanity check to make sure we understand these objectives, what is the best thing we should do? Should we trade or should we not trade to maximize either objective? Anybody?
We should trade.
We should trade, thank you. So what is the welfare if we trade? 5, thank you, Uri. And what is the gains from trade if we trade?
1.
1. And what is the welfare if we don't trade?
4.
4. And what is the gains from trade if we don't trade? 0. That's right. So for example, we have a great approximation to welfare if we don't trade, 4 compared to 5. But if we don't trade, we get 0, which is no approximation at all. Thank you for your participation. It's not even early for you. It's early for me. Okay. So what is our setting that we study in our paper? What we have is we have a multi-dimensional buyer and heterogeneous items. So we have n different items, and each item is owned by a single dimensional seller. So every seller is endowed with one item, and they only care about their single item. They have a value for their single item, again, drawn from a distribution that is known, it's independent, okay? So we have different sorts of items. And then we have one multi-dimensional constrained additive buyer with some feasibility constraint F. So what does constrained additive mean? It just means that they take their value for any set is the maximum subject to that feasibility constraint when you add up everything, okay? And as an example, this contains both unit demand and additive. Unit demand would just be the feasibility constraint of any set of size 1, so the maximum over anything in their set. Additive would be no feasibility constraint, so they just add up everything in their set. Okay, so constrained additive contains unit demand, contains additive, and for any feasibility constraint F. Any questions? This is the setting we're going to talk about for the rest of the paper, for the rest of the talk. Okay. So let's talk about what we're talking about when we talk about optimal gains from trade. There are two notions. There's first best and second best. These are economics terms if you're unfamiliar with them. Basically, we want to be able to implement the trade with a mechanism that has 3 properties that are desirable. 1 is Bayesian incentive compatible, 2 is ex post individually rational, and 3 is budget balanced. So what does that mean? 1, we want truth telling to maximize utility in expectation. 2, we don't want to regret participating. We don't want the buyers and sellers to regret participating. And 3, we don't want the platform to lose any money. They shouldn't have to inject money into the trade to make things work. And so if you're thinking from a computer science standpoint, the first best is unconstrained optimization. We're just maximizing gains from trade. And we're hoping that when we maximize it, subject to no constraints, that it satisfies properties 1 to 3. That's what first best is. Second best is saying, we're going to add the constraints. We're going to maximize gains from trade subject to constraints 1 to 3. We're going to make sure it satisfies 1 to 3. And so we ask, when we look at our unconstrained optimization, does it satisfy constraints 1 to 3? And we know the answer to be no from Myers and Satterthwaite, 1983, which says that if we look at how to best match everyone subject to unconstrained optimization, even for just bilateral trade, 1 buyer, 1 seller, 1 item, it does not, there's no way to satisfy constraints 1 to 3 in a mechanism. There's no mechanism to do this matching. There are examples for this. Okay, so the best we can hope for is this second best. We can't attain first best, so we then look at the constrained optimization problem of enforcing these constraints. What about second best? As with revenue, sometimes in special cases, we do know the second best mechanism. For example, Myerson-Satterthwaite tells us what it is in bilateral trade, but it's really complex, both the allocation and the payment. And as we move from bilateral trade to more buyers, more sellers, it only gets more complex. So what do you think I'm going to propose doing from here? Especially this audience, maybe Moshe?
Approximation?
Yes, why don't we look for simple but approximately optimal mechanisms? Okay, so what has been done previously?
So Kira, can I ask one question?
Yeah.
About budget balanced, are you okay with the mechanism getting money from the, the mechanism designer getting money from the trade?
I am, and I'm sure Uber is too. Yeah, so Michal is suggesting there are various types of budget balance. One is strong budget balance, where we're saying what the buyers pay should exactly equal what the sellers get. This is called strong budget balance. And then there's weak budget balance, which says it's okay if some money is left on the table and then the platform keeps it, which, as I'm saying, a lot of our platforms are probably very okay with that. So there's a lot of prior work in welfare, some really great work. As I said, it doesn't imply approximations for gains from trade, but the techniques can be useful. And so we know approximations for surprisingly broad settings. The broadest setting is this Collini-Baldacci et al. Paper from Wine 17, which does multiple XOS buyers and multiple additive sellers. So that's surprisingly general for a constant factor approximation for welfare. As for gains from trade, most of our results, I think this is missing quite a few. There's been a lot in AAAI recently, are in the trade size. So most of our results are in the optimal number of agents that trade, and then we talk about what if that number grows large. So they're asymptotic results. They're not worst case results for the exact number of agents in our market right now. And they say, okay, here's a mechanism that as the market grows large, then we'll get a good approximation. In terms of worst case gains from trade results, we only have very few, and they're only known for single dimensional markets, and I'll talk about them now. Any questions on this prior work before I go on to the gains from trade worst case? Okay. So the first result is from McAfee 08, and this is the median mechanism, which is just a fixed posted price mechanism. So this is just the platform says, here's a price P. The buyer thinks, do I want to buy at this price? Is my value higher than it? The seller thinks, do I want to receive this price? Is my value lower than it? If so, they trade. It's a very, very simple mechanism. We would love to use this mechanism in practice. And this achieves half of the first best. So the unconstrained opt. The second result I want to mention is by Blumrosen and Mizrahi, again in bilateral trade, and they get 1/e of the first best, and they use the seller offering mechanism, which basically they're giving the power of the mechanism to the seller as long as the seller only uses this one form of mechanism. So the seller says, what about this price? After they look at their value, and then the buyer says, okay, my value is higher or lower, and therefore I will trade or not. And they use this monotone hazard rate condition, which is basically a condition on the tail. The next result is this Wine 17 paper, which is a lot of what I'm going to be talking about today, which gives a 1/log 1/r approximation of first best, where R is the trade probability. So this is the probability that the buyer's value is larger than the seller's value. R is the trade probability. And again, they use a fixed posted price mechanism. And then there's also this paper by Brussel et al. From EC17, where they handle both the bilateral trade setting and the double auction setting. So this is where you have a bunch of buyers and a bunch of sellers, and there's only one type of item, and you're just trying to match them off. So it's also called a matching market. They don't have any assumptions, and they use generalized buyer and seller offering. So like the seller offering, but switch to the buyer. Okay. And then what we do is we present the first worst case approximation guarantee for a multi-dimensional buyer. Any questions there? Okay. So what is going to happen now that we're moving to the multi-dimensional setting that makes things more complex? First, I want to note that one thing we could do if we start with just this double auction matching market setting is we could think, what happens if one buyer owns all of the items? We can call this the super buyer utility. I'm just talking about a matching market to make this concept simple for a second. And so the super buyer utility compared to the matching market, a mechanism in the matching market, is we could say, let's look at everybody who matches, take all of their prices, minus the sellers. This is the super buyer's utility from the mechanism. Just the prices minus the seller's cost. We could do the same and say, what is the super seller's revenue? What if one seller owned all of the items? Then the revenue is going to just be the buyer's value minus the, sorry, these are switched. The buyer's value minus, okay, these are the, yeah, they're switched. Okay. The point being that you can bound the gains from trade by the super seller revenue and the super buyer utility if you switch these. And by just breaking down BI minus SJ into minus the prices plus the prices where it works out because of budget balance. Why is this important? We do know how to approximate both of these things, utility and revenue, in one-sided markets. But when we move to the multi-dimensional setting, things get more complex. So as a reminder, we can approximate welfare, even in multi-dimensional settings. We just talked about that in prior work. We can approximate revenue for such a multi-dimensional buyer. And we can approximate gains from trade in one-dimensional settings like matching markets with feasibility constraints. The problem, the added difficulty, comes from when we have these one-dimensional sellers and a multi-dimensional buyer. And the problem is going to be the incentives of all of these different sellers dealing with this multi-dimensional buyer. So the problem is the incentives on both sides when you have all these different sellers and one big buyer. Okay, so that's just supposed to be some intuition for where the challenge is going to come from. Okay, so we have two main results. The first result is that we're going to have a log 1 over R approximation. R here is the smallest over all of the items trade probabilities. So each item trades, each item is eligible to trade when the buyer's value is higher for that item is higher than the seller's value for that item. So this is the trade probability for an item, or the probability that item is eligible to trade. And R is the minimum overall, okay? So this could be a really low probability, but let's start here.
Kira?
Yeah.
You seem to index this, you have the same index for the buyer and the seller. Now, why is buyer I related to seller I? In what sense are they related?
Sure. So there are n sellers, each with one item, and then there's one buyer. And the buyer is interested in all the items. So the buyer has a value for each of the items.
Oh, you were talking about the super buyer case. Sorry, thank you.
Yeah, so in our setting for the rest of the talk, there is one buyer, and the buyer has a value for each of the items. We're no longer in the matching market setting. We're now in a multi-dimensional buyer setting.
Got it.
So that's, yeah. Okay. So our result is that there is a fixed posted price mechanism. So there's just prices for buyer, prices for seller. That achieves at least a 1 over log 1 over R fraction of the first best unconstrained gains from trade in this R, which is the minimum probability over all of the items that they're eligible to trade. Okay. So this is essentially a generalization of that Clini-Baldeschi et al. Paper to this multidimensional setting. That's the same approximation they got for bilateral trade. This applies to a broad class of downward closed constraints. Precisely, these are going to be exchangeable feasibility constraints, if you're familiar with that, but we'll get to that later. So this includes matroids, matchings, knapsack constraints, and the intersections of those. And we extend it as well to general downward closed constrained additive, but we're going to lose a log n factor there. So that becomes log n times log 1 over r. So that's our first result. And for more general constraints, we're going to have to use something a little less simple than a fixed posted price. It becomes a constrained fixed posted price mechanism. So what is the fixed posted price mechanism? We start with our multidimensional buyer who has a value for each item, and our sellers who each have a single item with a value for their item. We post prices for the buyer on each item. If he wants an item, he has to pay his price for the item. For the seller, for each seller, we also post a price for their item. If we want budget balance, then it better be that the buyer's price for each item is larger than the seller's price for each item. And then we say to each seller, okay, do you want to trade the item? Is the price sufficient? Is it more than your value? If it's not, then those items aren't eligible to trade. And similarly, we say to the buyer, do you want to buy each item? If not, those items also aren't eligible to trade. And then we ask the buyer, which set of items do you want to trade? Subject to your constrained additive constraint, which is the best, and he maximizes his utility. Okay, so after looking at this, the ones left are just items 1 and 3, or 1 and I rather, and he's going to maximize his utility among the eligible items. So if he's unit demand, he'll pick 1. If he has a broader utility constraint, maybe he'll buy both. And then he'll pay his posted prices for whichever ones he chooses, and the sellers will receive their posted prices. And it's budget balanced, it's weekly budget balanced, so long as these prices are larger. It's DSIC because it's just posted prices. It's individually rational because they only participated if their values were higher or lower. Okay, any questions about the mechanism? Okay. Our second result, so again, our first result was a log 1 over r approximation in this minimum eligible trade probability. Our second result is an unconditional approximation. So there's a simple Bayesian incentive compatible, individually rational, budget balance mechanism that achieves at least a 1 over log n fraction of the second best, no longer first best, but second best gains from trade for arbitrary seller and buyer distributions. Okay, so no longer is this an approximation dealing with R. And again, same types of constraints. This is again going to be exchangeable feasibility constraints. And here we also have general constrained additive, again, losing a log factor. Okay, and so the mechanisms we use here are again this fixed posted price, which again becomes constrained fixed posted price for the more general ones. We'll use a multidimensional extension of this buyer offering mechanism. And then we introduce a new mechanism called the seller adjusted posted price mechanism, which is necessary for approximation. Okay. So what is the seller adjusted posted price mechanism? So I'm starting with the setup of what the fixed posted price mechanism was, and I'm going to alter it to show you what the seller adjusted posted price mechanism was. Instead, what the seller adjusted posted price mechanism is for the buyer, we post prices which are a function of the seller's values. So rather than just post prices independent of the seller's values, we're going to use the seller's values to set the prices for the buyer, which allows us to earn a lot more gains from trade because it's dependent on the seller's values. So the buyer posted prices are a function of the seller's values. Okay. Now, we obviously need to set the prices for the sellers very carefully to deal with incentive compatibility since we're using their values to set the buyer's prices. So what we're going to do is, since the sellers are each single dimensional, they only have their value for their one item, we're going to use Meyerson's payment identity. So this function here is just Meyerson's payment identity. The thing is, if we're using Meyerson's payment identity, then we need to make sure that the allocation is monotone, or we can't use the payment identity. So this is our first challenge, and the way we deal with it is we introduce a concept called bimonotonicity. And our second challenge is, how do we make sure that this payment identity function is less than whatever function we're using? And this is the most difficult part of the mechanism, and this will be the thing I discussed last. So these are really the most technically challenging parts of the paper. Okay, so now I'm going to get into the first part, the log 1 over r approximation. Okay, any questions? Okay. So it looks like my first animation fails. So that's fine. Okay, so first we start with the first best gains from trade, which we can just divide into what is the best set to trade for our gain in buyer's value over seller's value. This is just what S star is. This is exactly what first best gains from trade is. It's just the buyer's value over the seller's value for that best set. Then what we do is we use this Collini-Baldacci et al. Bilateral trade approach to bound it by order log 1 over R events. We're dividing it into log 1 over R events. Again, R is the minimum over all of the items eligible trade probability. What are these events? Okay, I'm going to go to quantile space here. So what does that mean? This is the probability that a buyer has a value this high. This is the probability that a buyer has a value this high. So every buyer has a value that's at least this high. So the probability that a buyer has a value this high is 1. No buyer has a value all the way at the top of the distribution. So this is 0. This is quantile space. This is just the probability of where a buyer's value is. Okay. And so I'm going to divide quantile space into these theta ij's, just doing the standard divide by 2. So we have all of the 1 over 2 to the j's for log 1 over rj's, or order log 1 over rj's. Okay. For each theta at 1 over 2 to the j, I'm going to look at the event between 1 over 2 to the j and 1 over 2 to the j minus 1. And I'm going to say, what if the seller's value is in this range here? So again, if you're unfamiliar with quantile space, you can think of this, even though we're in the probability that a value is here, you can translate it back to value space, but it's easier to talk about it in the probability. So what is the probability that a seller's value is here in this range and that a buyer's value is at least this high? Why can't we just divide cleanly? Because if you just divide into log events, then you don't necessarily, even though you always have the buyer's value being higher than the seller's value, if it's in the optimal set, they don't necessarily divide cleanly at log points. So you need to look at some overlapping ranges. So we divide into log events that the seller's value is in some range, and then the buyer's value is at least the lower part of the range. Okay. So from Collini-Baldacci et al., our first best gains from trade is upper bounded by these order log events. And we can split into both in the buyer's quantile space and the seller's quantile space. Is that clear? Is the event clear? Okay. So from there, we can then split this into just the buyer's value minus this theta, and then the theta minus the seller's value. So I've just split up this BI minus SI. Now, our insight is that we modify this event into a new event. So now we keep the seller's value in the range, but we push up the buyer's value to be strictly higher than the seller's value. So now instead of having the buyer's value at least the 1 over 2 to the j minus I quantile, it's now at least the 1 over 2 to the j quantile. And because we're in quantile space, which means that the probability that the buyer's value is this high is 1 over 2 to the j minus 1, and the probability that the buyer's value is this high is at least 1 over 2 to the j, then the probability of this event is what compared to this event? So think of this as a half, and think of this as a quarter.
At most a quarter apart, the probabilities.
So this is now 1/2 what this is. So we just took the buyer's value and chopped it in a half higher. We just divided it by a half in quantile space. Does that make sense? We've divided quantile space into halves and halves and halves, and we just moved it up to the next half. So this is just the probability of this event is exactly 1/2 what this one is. So if the probability that the buyer's value was at least this 1 over 2 to the j minus 1, if this was just 1/2 before and this is 1/4, this used to be 1/2 and now this is 1/4. And 1/4 is 1/2 times 1/2. Okay? So that means that we can replace these events with our new events and a factor of 2. And now we have a clear separation between our buyer and our seller value. And what does that mean? That means in our new events, we know that the buyer's value is at least theta ij, the seller's value is below theta ij. Similarly, in our mirrored events, they're separated by this theta ij prime. And so we replace them just by these events. Okay? So again, we went from these events to just part of the event, which is where the seller and buyer's value is. Okay. And now I'm just going to focus on basically one term in the benchmark. So this is just the final part of the benchmark that I had. What I want to say is you can't use a fixed posted price for this part of the benchmark. You can't just set the buyer's price equal to the seller's price, which the best thing you'd want to do here would be to set it to that theta ij, because the buyer is going to maximize his utility. And what you want here is to maximize this theta ij minus si, which is not the buyer's utility. It's the opposite, okay? And so in terms of maximizing the buyer's utility, it's actually quite easy for these other terms, this bi minus theta I. So these terms are easy to handle. It's these terms which are difficult to handle. And so I'm going to talk about how to handle these terms. And so our idea is to instead bound this by using the profit inequality. And so what we do is we just choose our variable carefully. We choose this to be our VI in the profit inequality. And this becomes, let's maximize a bunch of VIs. And we use the profit inequality here. I'll show you how if you are not a profit inequality expert like some of you, because I don't expect you to be. Okay, what's the profit inequality? You have a bunch of items, and your goal is to pick one item and maximize the value of the item that you pick. There is some profit who knows exactly what the best item is going to be. She always knows the max. Right here, we're just talking about picking one item. You're a gambler. You know the distribution for each item. The order is adversarial, and it's arriving online. And so as they arrive, you're going to inspect each item. You're going to see V1. You don't know the other Vs. Then you'll see V2. And you have to decide as they arrive whether to take it or pass forever. So you see V1, no. You see V2, no. Then you see V3 and you say, okay, I'll take it. And so your goal is to compete against this profit, get the best approximation. And so this was originally introduced by Kringle, Sucheston, and Garling. And then the first approximation was known by Samuel Kahn. It was brought to mechanism design by Hajiagi et al. And so what we know is that we have a threshold algorithm where you can accept a box, accept an item, exactly if it's over a threshold, where this threshold is just 1/2 the expected max, which you can compute because you know all the distributions. And this is given by Kleinberg-Weinberg. And so let's go back to looking at our benchmark, that one component of our benchmark. That single term that we wanted to deal with looked like this, where I've taken out the theta and called it pi. Okay, so we're gonna, again, translate our VIs for the profit inequality into this term from the benchmark. And here's what I'm gonna say. I'm gonna say that I'm going to map it by saying that VI is greater than our threshold exactly when BI beats its price, this price PI, and PI minus SI is larger than T. Okay, this threshold. And so what I want to do is I want to set a price. Theta IB is going to be the price for the buyer at PI. And theta IS is going to be the price for the seller at PI minus T. And so what we see is that some VI, some item beats its threshold exactly when some item is traded. Okay, so if some item beats its threshold, then, so how do we know that a VI is greater than T? Well, this indicator better not be 0, so BI is greater than PI. This better not be 0, so pi minus, this better be at least t, so pi minus si is at least t. So bi beats its price. Similarly, si is willing to take its price by this. And so there is some item that's willing to trade. Does that make sense? If we set these prices, then there is some I that's willing, there's some I that's willing to trade. And so if some I is willing to trade, if some I beats its threshold in the profit inequality, then you're good to go. So this is a mapping. Questions? I see confused looks.
So Kira, can you explain what's the relation between this sequential decision making and the problem you talked about before with G, in which the values are separate, separate.
So it doesn't have to be sequential. It's sort of the same mapping as when you map to revenue, except for here you just need to set up the prices. It doesn't matter which order you go in. As long as some item is willing to trade, then there's some box in the adversarial ordering that beats it. So it doesn't matter which order the buyer picks in, even though it's not arriving online. There's a bunch of items in front of him. One of them is willing to trade. We don't care which one maximizes his utility. That was our problem before, is he was maximizing his utility and it wasn't working out because we wanted to maximize for the seller.
Okay. Thanks.
And so it's sort of the same as the buyer maximizing his utility is like an adversarial ordering. We don't have control over the ordering. But as long as something is eligible to trade, as long as the beats this threshold, that's how it sort of aligns with the profit inequality. Okay. So that was for the one item case, which corresponds to unit demand, is there's just a single non-adaptive threshold. Unfortunately, we don't have a lot of non-adaptive single threshold results. For the constrained additive case, we do have this online contention resolution scheme results from Moran Feldman, Ola Svensson, Enrico Zinklusen. And basically what it says is that as long as our feasibility constraint has this delta eta exchangeability, which is for matroids and matchings and knapsack, then there is an approach that has basically non-adaptive thresholds plus a feasibility constraint. So this is where that constrained fixed posted price comes in, because you have this extra feasibility constraint, which is this F prime. And you basically say that the buyer can only buy things using this extra feasibility constraint. So you still have a similar fixed posted price mechanism, but you're constraining what the buyer can buy from this extra feasibility constraint. Now, so it's a similar mapping from that type of profit inequality result. But when you move to downward closed, there is a profit inequality result from Aviad Rubinstein, but it's highly adaptive, so that's not going to work. And in fact, Moshe et al. Have a lower bound, so we know that such an approach is not going to work. So instead what we do is we use a different result that's sort of like bundling, but instead of bundling the value, we bundle the number of items. So what we do is we divide the same VI variable, the sum of it, into buckets. And what we do is we show that the optimal size that the profit wants to take concentrates. And so we look at what that optimal size is, and then we say to the buyer, you need to take at least this H many items. You can buy whatever you want as long as you take at least H many items. So this is another type of constrained fixed posted price. Here are your prices, but you need to buy at least H items. And we choose H by looking at this concentration. So that's how we do general downward closed. Okay, any questions about that? Okay, so I'm going to move on to the unconditional approximation from there, if that's okay. Okay, so now we're going to go from our log 1 over R approximation that we used by dividing into log one over R events and mapping the profit inequality to now get an unconditional log n approximation. So what do? We start with the second best now. Before we had an approximation to the first best, now we're using the second best. We're going to divide into, again, the super buyer and super seller, the way I showed before. This comes from Brussels et al., except for we very barely tweak their proof to extend to the multidimensional setting. For the buyer setting, this is the buyer procurement auction. Again, this is where you have a super buyer, and basically the buyer is the mechanism designer here. And for Opt-S, that's the super seller auction. So you're trying to bound either the buyer utility or the seller revenue. However, you need to use a mechanism that still deals with incentives for both sides of the market when you do that. So you want to get gains from trade that bounds that quantity and deals with incentives for both sides of the market. Bounding the buyer procurement auction is not very difficult. For the next part of the talk, I'm basically just going to illustrate it for unit demand, but obviously it extends. So what we do is that since sellers are single dimensional, we can write out this optimal quantity. It just looks like basically, this is what profit looks like in the single dimensional setting, but flipped, okay? So if you were to have, this is the seller and this is a bunch of buyers, this is what the optimal profit would look like, but instead, because this is a buyer and this is sellers, it's flipped. So here we have what's analogous to virtual cost using something like Meyerson's virtual value, where it's just, in case you haven't seen this before, it's like Meyerson's function, but instead you have the seller's value plus something like that extra term for the seller's CDF, okay? And so what the mechanism is it basically says, let's trade the item in unit demand that maximizes this buyer's value minus this virtual seller's cost. And the sellers get the payment identity because they're single dimensional, and the buyer pays the virtual cost. And there's a transformation to make this strongly budget balanced and Bayesian incentive compatible. So you might look from first glance like it's ex ante weekly budget balanced because you've got virtual costs and this should be an amortization of the values, but they show in their paper, Brussels et al., that there is a transformation when they introduce this mechanism. Okay, so this is basically just importing a result from their paper to bound this quantity. Any questions there? Okay, so we split into the buyer part and the seller part. We bounded the buyer part with this generalized buyer offering mechanism, which comes from Brussels et al. Now what we do is we split the seller part from the super seller auction into the first best gains from trade from some set H and the optimal seller revenue from some set L. And in particular, I'm going to define those sets to be the likely to trade items and the unlikely to trade items. The way we do this is we use basically an analog of the marginal mechanism lemma that we all know and love from Hardy-san, Sai Huang. And the idea is just the same. Instead of having welfare and revenue, now we have gains from trade and super seller revenue, okay? So that's how we split into gains from trade and super seller revenue. And the reason that we're dividing into these likely to trade items and unlikely to trade items is you'll remember that we had our prior approximation in terms of R. What was R? It was the minimum trade probability. Here we're saying all items are at least 1 over n likely to trade. So our minimum trade probability is 1 over n, which means this part will get a log n approximation. So that was just, we engineered the split that way. We used our first result. We get a log n approximation using our fixed posted price or constrained fixed posted price mechanism, depending on the feasibility constraint. Okay, so we've handled these likely to trade items and approximated the first best gains from trade of this part. So all that's left is to handle these unlikely to trade items and handle the super seller revenue of the unlikely to trade items. Okay, Any questions about that so far? I want the high level to be really clear. Please ask questions. Okay. So now what's left to show is that we can also get a log n approximation here using our new mechanism, seller adjusted posted price, which I mentioned in the beginning. Okay, so this is what remains to show. Okay, so here we're in this branch of the proof sketch. We're bounding the unlikely to sell items, L meaning low trade probability, the super seller auction of them. Okay, so again, here's our depiction of the super seller auction. There's one super seller who owns all the items, is the mechanism designer, and this is the quantity we're bounding. We still need the mechanism we design to have incentives for both sides and get gains from trade. Okay, that's the quantity we're bounding. Okay, what we know from Tsai and Zhao 2019, which is their paper on profit, is that we can bound the optimal superseller of any set by log L times basically selling each item individually. Okay, and so why is this different from what we already know? Basically, the only difference is that it's now profit as opposed to just revenue. So we have the buyer's value, virtual of the buyer's value minus the seller's cost. Okay, so this is the Myerson virtual value, and it's the same log gap that we know from Hardy-san. So all we've done is we've taken the seller's revenue and we've split it into item pricing, essentially, just the best possible revenue from each item. Make sense? Was there a question on this? No, okay. Okay, so now I want to bound that quantity using the seller adjusted posted price mechanism. Again, let me say what that was. We had that buyer posted prices are a function of seller values. The seller's price would use the Myerson payment identity. Our challenge was, is the seller's allocation monotone and is it budget balanced? Notice that we're only selling those unlikely to trade items. That's what's first. The second is that we're going to enforce that our prices are bi-monotonic. This is a concept we introduced. If it sounds unfamiliar, I just made it up. What that means is that first, we want our prices, of course, to be satisfactory to our seller. Second, we want our prices to be non-increasing in the seller's own value. This is sort of the normal monotonicity we expect in prices, and non-decreasing for all of the other seller's values. So this is the price for the buyer for item I. We want, if the seller for item I increases his price, it shouldn't help. If it increases his cost, it shouldn't, sorry. This is the price for item I, and we want, if the seller increases his value, we don't want it to help. And we also don't want the other seller's values to mess with it. Does that make sense? When we have this, what it does is it makes the seller's allocation rule monotone. And then we can use Myerson's payment identity. So if we enforce that our prices are bi-monotonic, then what we can do is we can have budget balanced seller adjusted posted pricing, and we can get at least the gains from trade that we want, at least constant of just the single term, which then gives us a log term in general. Okay. The part that I'm hiding is this budget balance part, which is the hardest part of the whole thing. And it's extremely technical and not appropriate to show in a talk. But basically what you have to do here is you have to take the allocation for each of the sellers and say that it won't be too high and it also won't be too low. And by bounding it within a range, then you can say that because it's within a range, the seller's payment is appropriately low, that it will be below the buyer's payment. And basically that proof is extremely technical, and I think that finding a way to improve the budget balance proof is a great direction for further work. Okay, so just to review, our proof sketch was we divided it into the super buyer utility and the super seller revenue. We bounded the super buyer utility with the generalized buyer offering mechanism. We bounded the super seller utility by using the marginal mechanism lemma to divide it into the first best gains from trade of the likely to sell items and the super seller revenue of the unlikely to sell items. We bounded the first best gains from trade using our first result, now that our minimum trade probability is over 1 over n. And we bounded the unlikely to trade items revenue by first turning it into each item's item pricing revenue, and then using the seller adjusted posted pricing. I do want to comment that the seller adjusted posted pricing is necessary. We have some examples in the paper that basically say that without the seller adjusted posted pricing, you can, it's an unbounded approximation just using fixed posted pricing and generalized buyer offering mechanism. So this sort of crazy mechanism is necessary. I think it's a really interesting mechanism, and I think the fact that it was really hard to analyze makes it even more interesting because I think there's got to be an easier way somewhere. Yeah.
So Kira, the seller adjusted posted price, is it as if there was a super seller that posts prices, or is it different?
No, so what's happening is the platform is determining some function. It's determining a function of, for each item, of all of the seller's prices. So it's kind of dealing with the buyers as if there's a super seller. But then in order to handle the incentives of each of the sellers separately, it needs to give them Meyerson's payment identity. But then in order to deal with budget balance, so that part's not too hard, just dealing with the incentives. You need your payment function to have this bimonotonicity property, or rather it's sufficient. And basically we just prove that it exists. But the hard part is then, how do we make sure that everything is budget balanced? And what you need to do is you need to bound the allocation and then do a lot of technical manipulation to say, it all works out, but it's pretty messy.
So these bimonotonic prices exist, but it's not the outcome of the super seller prices. These are two different things.
Correct.
Okay.
It's unfortunately not very elegant. Yeah. Or were you raising your hand or no? Okay. So I gave you a log approximation in the simplest multidimensional setting, which is kind of unsatisfying, given that we know constant factor approximations for two-sided welfare, we know constant factor approximations for one-sided multidimensional revenue up to pretty complex settings. So is log the right answer? I don't know, but the question of finding a lower bound for our mechanism reduces to solving the gap of first best versus second best in the single dimensional matching market. So we show a reduction that says, if second best gains from trade, C approximates first best in the single dimensional matching market, then our mechanism is a 2C approximation to first best gains from trade. Right now, it's a log n approximation to second best gains from trade. But if there's a C approximation for a constant for anything, whatever C is, then our mechanism is a 2C approximation. So if you think that first best and second best are constant factor apart in the single dimensional matching market, then you think that our mechanism is a constant factor approximation. Similarly, finding a lower bound to our mechanism is at least as hard as separating them in the single dimensional matching market. And very, very little is known about the gap in the single dimensional matching market, even in bilateral trade. So this is like a huge open problem that I think people should be working on, and also my excuse for why I don't have a lower bound for you. So to summarize, we approximate gains from trade in the multidimensional two-sided market with one constrained additive buyer and n one supply sellers. We give this log 1 over R approximation, where R is the minimum eligible trade probability using only fixed posted price mechanisms. And then we give this unconditional log n approximation using these 3 different mechanisms. And we lose another log n in both if the feasibility constraint isn't exchangeable, which many feasibility constraints are exchangeable. So open problems, more general settings, obviously. We only deal with one buyer, some multiple buyers, and multi-dimensional sellers would obviously be nice. We only have single dimensional sellers. Can we get a better approximation ratio with seller adjusted posted pricing? It seems like a very, very powerful mechanism. And it seems like our analysis is loose in a bunch of places, but as I said, it's pretty complex. And most interestingly, I think, is understanding the first best, second best gap, even in bilateral trade or double auctions. I think all that's known is that they're at least a factor or 2 apart, but maybe Shachar knows more. Yeah, okay, thank you.
Great. Thanks very much, Kira, for the wonderful talk. So I guess we can take questions.